welcome. Find yourself a comfortable place. Perhaps you're lying down, ready to rest. Perhaps you're simply seeking a moment of calm in your day. Wherever you are, whatever time it is, you're welcome here. Tonight, we're going to follow a single drop of water on its journey. Not a rushed journey, not an exciting adventure, simply a journey. The kind that happens every day, in every part of the world, without fanfare, without urgency, just the quiet, eternal movement of water through our world. This is a story that has no beginning and no end. It's a circle, or perhaps more accurately, a cycle. And like all cycles, we can step into it at any point. So let's begin where many of us feel most connected to water, with rain. Imagine, if you will, a droplet forming in a cloud, high above the earth. Not falling yet, just forming, gathering, becoming. Our story begins, as many stories do, with something very small, impossibly small. A single molecule of water floating in the atmosphere, invisible to any eye. This molecule, let's call it our protagonist, though it has no awareness, no consciousness. This molecule is one of trillions upon trillions in the air around us at any moment. Water vapor is always present in our atmosphere. Always. Even in the driest desert, there are water molecules suspended in the air, waiting. The air can hold different amounts of water, depending on its temperature. Warm air, with its faster-moving molecules, can hold more water vapor. Cold air, where everything moves more slowly, more deliberately, holds less. Our water molecule drifts. It has been drifting for some time now. Perhaps it evaporated from the ocean 3 days ago. Perhaps it was breathed out by a plant, released through tiny pores in a leaf. Perhaps it rose from a lake or a puddle, or from the soil itself. The origin doesn't matter much to the water molecule. It simply is. And so it drifts, carried by air currents we cannot see, riding on invisible rivers of wind. Sometimes rising, sometimes falling, always moving in the great atmospheric currents that wrap around our planet. Then, something changes. The air begins to cool. Perhaps our water molecule has risen high enough that the temperature has dropped. Perhaps it has traveled to a region where cold air from the poles meets warm air from the equator. Perhaps it's evening, and the sun's warmth is fading from the sky. Whatever the cause, the air grows cooler. And as it cools, it can hold less water vapor. The molecules begin to slow their constant vibration. They draw a bit closer together, not yet condensing, but preparing to. For condensation to truly begin, water molecules need something to gather around, a nucleus, a tiny particle suspended in the air. This could be a grain of dust, lifted from the earth by wind. It could be a crystal of salt from sea spray. It could be a fragment of pollen, carried on the breeze. It could even be a tiny particle of smoke, from a fire, or a volcanic eruption, or the exhaust of human activity. The atmosphere is full of these particles. We call them condensation nuclei, and they are constantly present, invisible, waiting. Our water molecule encounters one such particle. Perhaps it's a microscopic grain of dust from the Sahara Desert, carried across the Atlantic Ocean by the trade winds. This dust particle is rough, textured at the molecular level, with plenty of surface for water molecules to cling to, and so our molecule does exactly that. It clings. One molecule alone is not enough to see, not enough to feel, not enough to fall. But our molecule is not alone for long. The air continues to cool, and more water molecules find the dust particle. They begin to cluster around it, attracted by the weak electrical forces that exist between water molecules. Hydrogen bonds, they're called. Each one is weak, but together they are enough. 2 molecules become 3, 3 become 5, 5 become 10. The droplet grows, molecule by molecule, in the quiet darkness of the cloud. This process happens slowly, not by human standards perhaps. A water droplet in a cloud can form in minutes or even seconds. But on the molecular scale, where time operates differently, where movements and collisions happen in fractions of a second, this is a patient process, a gradual accumulation. The droplet grows to 1,000 molecules, 10,000, 100,000. It becomes large enough that if we could see it, it would appear as the tiniest speck of moisture. Still not enough to fall, still held aloft by the gentle upward currents of air within the cloud. The cloud itself is beautiful, though we cannot see its beauty from inside. From the ground, it might appear as a grey sheet across the sky, or perhaps as white billows if the sun catches it at the right angle. But from within, it is simply cool, moist air, filled with countless droplets all forming at once. Our droplet continues to grow. 1 million molecules, 10 million. It's now large enough to be called a true cloud droplet, though still far too small to fall as rain. Cloud droplets are tiny, typically only about 10 to 20 micrometers in diameter. That's smaller than the width of a human hair. 100 of them could line up across a single millimeter, and our cloud holds billions of these droplets, all suspended, all waiting. Time passes in the cloud. Our droplet drifts with the air currents, rising and falling within the cloud's interior. Clouds are not still things, though they may appear so from the ground. Inside, there is constant motion. Warm, moist air rises from below, cooling as it ascends. Cooler air sinks back down. The cloud itself may be traveling across the sky, carried by winds at its altitude. Our droplet encounters other droplets. They brush against each other in the misty interior of the cloud. Sometimes, they collide with enough force to merge, combining their waters into a single, slightly larger droplet. This is called coalescence. But even with coalescence, our droplet remains small, too small to overcome the upward currents of air that hold it aloft. It needs to grow larger still, much larger. In some clouds, particularly in tropical regions, where temperatures remain above freezing throughout, droplets grow mainly through collision and coalescence. Larger droplets fall faster than smaller ones, and as they fall through the cloud, they collide with smaller droplets, gathering them up, growing steadily larger. But in other clouds, particularly in clouds that extend high into the atmosphere, where temperatures drop below freezing, something different can happen. Even though temperatures in the upper reaches of the cloud have fallen below 0 degrees Celsius, many of the water droplets remain liquid. This seems impossible. Perhaps, how can water be liquid below its freezing point? But this phenomenon, called supercooling, is common in clouds. The tiny droplets, so pure and so small, can remain liquid well below freezing, sometimes down to -40 degrees Celsius. But they are unstable, waiting for the right trigger to freeze. Some droplets do freeze, though. Perhaps they encounter a particle of dust that serves as a freezing nucleus. Perhaps they simply reach a temperature where they can remain liquid no longer. Whatever the cause, they transform from liquid to ice, forming ice crystals. These ice crystals are different from the liquid droplets in an important way. At these cold temperatures, the air is more saturated with respect to ice than with respect to liquid water. This means water molecules in the air around an ice crystal are more likely to attach to the crystal than to a liquid droplet, and so the ice crystals grow. They grow faster than the liquid droplets around them. They pull water vapor from the air, and they pull it from the nearby droplets, which evaporate to maintain equilibrium. Perhaps our droplet encounters an ice crystal. Perhaps some of its molecules are pulled away, evaporating from the droplet's surface and then condensing onto the ice. The droplet shrinks slightly, while the ice crystal grows. Or perhaps our droplet itself freezes, transformed by collision with an ice crystal, or by the pure cold of the upper cloud. Let's imagine that our droplet remains liquid for now, but the cloud around it is transforming. More and more ice crystals form. They grow larger, developing the intricate six-sided structures that give snowflakes their beauty. These crystals begin to fall, slowly at first, through the cloud. As they fall, they collide with our droplet. Some pass by, but eventually, one crystal meets our droplet directly, and the droplet freezes onto the crystal's surface. Our water, which was a droplet, is now part of a snowflake. The snowflake continues to fall through the cloud, gathering more supercooled droplets as it descends. Each collision adds more ice to its structure. It grows heavier. The intricate crystalline structure becomes more complex, each arm of the six-pointed star developing its own branches and sub-branches, all following the same fundamental geometry that ice molecules prefer. The snowflake falls faster now. It has become heavy enough that the upward air currents can no longer support it. Gravity, that patient, ever-present force, pulls it downward. As it descends through the lower regions of the cloud, the temperature begins to rise. Not suddenly, not dramatically, just gradually, as the snowflake enters air that is closer to the Earth's surface, air that has been warmed by the sun's energy absorbed by the ground. At some point, the temperature rises above freezing. The snowflake begins to melt. The ordered crystalline structure, which formed so beautifully in the cold upper cloud, begins to break down. The rigid lattice of ice becomes the flowing chaos of liquid water once more. The snowflake melts completely, becoming a raindrop. And our water, which began as a single molecule, which became part of a cloud droplet, which froze into a snowflake, is now part of a raindrop falling through the air. Raindrops are not shaped like tears, despite how they're often drawn. They're not pointed at the bottom and round at the top. Small raindrops, those less than a millimeter in diameter, are nearly perfect spheres. Surface tension, the same force that lets small insects walk on water, pulls the droplet into the most compact shape possible. Our raindrop is larger than this, though. It formed from a snowflake, which gathered many smaller droplets. It might be 3 or 4 millimeters in diameter. At this size, air resistance begins to matter. As the raindrop falls, air pushes up against its bottom surface. This pressure flattens the bottom of the drop, giving it a shape rather like a hamburger bun, rounded on top, flattened on the bottom. The drop oscillates slightly as it falls, its shape vibrating between different configurations. But the oscillations are gentle, damped by the drop's surface tension and its interactions with the air. The raindrop falls at what we call its terminal velocity. This is the speed at which the upward force of air resistance exactly balances the downward force of gravity. For a raindrop of our size, this speed is about 9 meters per second, about 20 miles per hour. Fast, but not impossibly so. Faster than you'd want to run, but slower than a car on most roads. The journey from cloud to ground might take several minutes, depending on the height of the cloud. Our raindrop falls through layers of atmosphere, each with its own temperature, its own density, its own subtle characteristics. It falls through air that may contain pollen or dust, or the spores of fungi. It falls through air that birds have flown through, that insects navigate, that carries the sounds of the world below. But the raindrop is indifferent to all of this. It simply falls, pulled by gravity, shaped by air resistance, on its inevitable journey downward. Sometimes, the raindrop encounters other raindrops. When two drops collide, they may merge, combining into a single, larger drop. Or they may bounce apart, surface tension keeping them separate. The outcome depends on many factors: their relative speeds, their sizes, the exact angle of collision. Our raindrop might collide with several others on its way down, growing slightly larger with each merger. Or it might fall alone, untouched, through all those thousands of meters of air. As the raindrop approaches the ground, the air grows warmer, denser. The temperature has risen significantly since the cold heights of the cloud. If our rain is falling in spring or summer, the air near the ground might be warm enough to evaporate some of the smaller raindrops, shrinking them before they land. But our drop is large enough to resist this evaporation. It continues its descent. Below, the surface of the earth approaches. Perhaps it's a forest, with leaves waiting to catch the rain. Perhaps it's a field, with soil ready to absorb the water. Perhaps it's a city street, with pavement that will send the water flowing toward drains. Perhaps it's the surface of a lake or an ocean, where the raindrop will rejoin the vast body of water from which it once came. The moment before landing is not dramatic. There is no sound yet, no impact, just the steady, inevitable approach of water to earth. The raindrop has no awareness of its impending arrival. It simply is, and it falls. And then, our raindrop strikes a leaf. The impact is gentle but real. The kinetic energy of the falling drop transfers to the leaf, causing it to bend slightly under the blow. The drop deforms on impact, spreading out across the leaf's waxy surface, which has evolved specifically to handle water. For a moment, The drop holds together, though it's now flattened against the leaf, spread into a thin film. Surface tension tries to pull it back into a droplet shape. The leaf's surface, with its microscopic structures, guides the water. Then, slowly, the water begins to move. Gravity still acts on it, pulling it toward the lowest point on the leaf's surface. The water flows, not in a rush, but in a slow migration across the leaf, following the contours, the veins, the natural channels that evolution has carved into this small green platform. Other raindrops have landed on the same leaf. Their waters meet, merging into a larger pool. The combined water grows heavy enough to overcome the adhesion to the leaf surface. It forms a droplet at the leaf's edge, hanging there for a moment in perfect suspension, and then it falls. Another small journey. A fall of perhaps 1 or 2 meters from the leaf to the ground below. The droplet lands on soil, rich, dark soil, full of organic matter from decomposing leaves and the work of countless microorganisms. This soil is porous, not solid, between the grains of mineral matter. The sand, silt, and clay that make up the soil's body. There are spaces, pores, voids filled with air or water. Our water seeps into these spaces. This process is called infiltration. The water moves through the largest pores first, pulled by gravity and by capillary action. The tendency of water to climb into narrow spaces due to its attraction to soil particles. As the water infiltrates, it pushes out air that was in the pores. It flows downward, but not in straight lines. The path is tortuous, winding through the complex 3-dimensional maze of the soil's structure. Sometimes the water flows through a large pore and moves quickly. Sometimes it enters a small pore and moves slowly, held by strong capillary forces. Some of the water is taken up by plant roots. The roots of trees, grasses, shrubs, all are drawing water from the soil, pulling it into their vascular systems to be transported up through their stems and into their leaves. Perhaps some of our water molecules are absorbed by a root hair, the tiny, delicate extensions that increase a root's surface area for absorption. But let's imagine that most of our water continues downward, seeping through the layers of soil. As our water descends, it passes through different soil horizons. Near the surface is the O horizon, rich in organic matter. Below that is the A horizon, where organic matter mixes with minerals. Deeper still are the B horizon, where minerals accumulate, and the C horizon, where weathered parent material transitions to bedrock. Our water carries dissolved minerals with it. As it seeped through the soil, it picked up ions, calcium, magnesium, potassium, sodium, and carried them along in solution. The water is no longer as pure as it was when it fell from the cloud. It has become mineral water, bearing the chemical signature of the soil it has passed through. The descent takes time, not hours, but days, perhaps weeks. The water moves slowly through the smaller pores, sometimes almost stopping where pore spaces are tiny, sometimes flowing more freely through cracks or channels in the soil. Eventually, our water reaches a layer where all the pores are already filled with water. This is the water table, the upper surface of the zone of saturation. Below this point, the water isn't moving quickly downward anymore. It's part of the groundwater, the vast reservoir of water that exists beneath the Earth's surface. Time moves differently for groundwater. Our water might rest here, in the dark, saturated Earth, for years, or decades, or even centuries. There is no urgency underground, no wind to carry water vapor, no surface flow to rush water toward the sea, just slow, patient movement through rock and soil, following the gentle gradients of the water table. The water moves laterally now, flowing very slowly toward lower elevations. It might travel only a few meters per year, or even less. The speed depends on the permeability of the rock or soil it's moving through. In gravel or fractured rock, water can move relatively quickly, perhaps a meter per day. In clay or solid granite, movement might be measured in centimeters per year. Our water is not alone down here. It's part of an aquifer, a body of saturated rock or soil that can store and transmit water. Other water surrounds it, water that fell as rain decades or centuries ago, water that's been on a similar journey, water that waits in the darkness. Sometimes, groundwater emerges at the surface again. If the water table intersects the land surface, water seeps out, forming a spring. Groundwater also feeds into the bases of streams and rivers, providing the base flow that keeps them running even when it hasn't rained for weeks. Let's imagine that our water, after months or years underground, emerges from a spring on a hillside. The spring is a quiet place. Water seeps from between rocks, from the base of a clay layer that the water cannot penetrate, flowing out onto the surface. The water is cool, having been insulated from the surface temperature variations by its time underground. It's clear, filtered by its passage through soil and rock. It carries dissolved minerals but no sediment, no organic matter. It's clean in a way that surface water rarely is. The water from the spring forms a small pool and then a trickle. The trickle becomes a stream as more and more water emerges from the spring, joining together, following the path of least resistance down the hillside. Our water is now part of a stream. It flows over rocks smoothed by centuries of water passage. It flows through gravel beds, around boulders, through riffles where the water becomes shallow and fast, and through pools where it slows and deepens. The stream is alive with activity. Aquatic insects walk on its surface or cling to rocks in the current. Fish dart in the pools. Plants grow along its banks, their roots drinking from the flowing water. Algae coat the rocks, green and slippery, performing photosynthesis in the dappled sunlight that filters through the tree canopy above. Our water molecules are mixed thoroughly with countless others in the stream's flow. They travel together, tumbling in the current, sometimes near the surface where they can feel the air above, sometimes deep in the stream where they flow along the rocky bottom. The stream follows the lay of the land, always seeking the lowest path. It curves around obstacles, cuts through softer earth, joins with other streams. Each tributary adds more water, and the stream grows. Gradually, imperceptibly, the stream becomes a river. There's no exact point where this transition happens. It's simply that the flow is now larger, deeper, wider. The banks are farther apart. The current is strong and steady. The river flows through different landscapes, perhaps through forest, where trees lean over the water, perhaps through meadows, where the banks are lined with grass and wildflowers, perhaps through farmland, where the water that flows here may be used for irrigation, diverted briefly to water crops before returning to the river downstream. The river's speed varies with the slope of the land. In steeper sections, it flows quickly, turbulent and white with air bubbles churned into the water. In flatter sections, it flows more slowly, more peacefully, the surface barely rippling. Our water molecules remain in the river for days or weeks, traveling tens or hundreds of kilometers. They've moved from the hillside spring to the valley floor, always descending, always pulled by gravity toward the lowest point in the landscape. And for rivers on most continents, the lowest point is the sea. The river widens as it approaches the ocean. The gradient flattens. The flow slows. Salt water from the ocean pushes up into the river's mouth at high tide, mixing with the fresh water flowing down. This mixing zone, where river meets sea, is called an estuary, and it's a unique environment, neither fully fresh nor fully salt, constantly changing with the tides. Our water molecules flow into the estuary. They mix with water that is salty, that has come from the ocean. They pass through marshes and mudflats, through waters rich with nutrients carried from the land, waters that support vast populations of fish and birds and invertebrates. And then, finally, the water flows out into the ocean proper. The river's current dissipates in the vastness of the sea. The boundary between river and ocean blurs and disappears. Our water, which fell from a cloud, which seeped through soil, which flowed in a spring and a stream and a river, has now returned to the ocean. The ocean is vast, incomprehensibly vast. It covers 71% of the Earth's surface. It contains 97% of all water on our planet. The ocean is deeper than the highest. Mountains are tall. Its trenches descend more than 11 kilometers below sea level, into regions of crushing pressure and utter darkness. Our water molecules are now part of this vastness. They are lost in it, mixed with countless other molecules, indistinguishable, unmarked. The water near the river's mouth is relatively shallow. Sunlight penetrates all the way to the bottom. Nutrients from the river support rich biological communities. But our water molecules won't stay here. The ocean is always moving, and they will be moved with it. The ocean has currents, rivers within the sea. Some are driven by wind, the surface waters, pushed by the constant trade winds, or by the westerlies. Some are driven by differences in temperature and salinity, the thermohaline circulation that moves water through the depths of the ocean in currents that take centuries to complete a cycle. Our water molecules might be caught in a surface current, flowing along the coast, moving with the gyre, the large circular current pattern that characterizes each ocean basin. Or they might sink, becoming part of the deep water that flows slowly along the ocean floor, moving from the poles toward the equator over decades or centuries. Let's imagine our water molecules remain near the surface, in the warm upper layer of the ocean that's been heated by the sun. Here, they drift with the currents, traveling slowly across the ocean. Days pass, weeks, months. The water might travel hundreds or thousands of kilometers, circling in the gyre, moving with the persistent currents. The surface ocean is full of life. Microscopic phytoplankton drift in the water, performing photosynthesis, the foundation of the ocean's food web. Zooplankton graze on the phytoplankton. Small fish eat the zooplankton. Larger fish eat the small fish. The complexity and abundance of ocean life is staggering, though most of it is invisible to casual observation. Our water molecules are part of this living system, though they don't become part of the organisms themselves. They remain in the surrounding seawater, in the medium that supports all this life. The water is salty, 3.5% salt by mass on average, mostly sodium and chloride, but also traces of nearly every element on the periodic table. The ocean is a solution, and our water molecules are the solvent, the medium in which all these minerals are dissolved. Time passes. The sun traces its path across the sky, higher in summer, lower in winter. The ocean's surface temperature changes with the seasons. In summer, the upper layer warms, and a strong thermocline, a boundary between warm surface water and cold deep water, forms. In winter, the surface cools, the thermocline weakens, and mixing can bring deep water to the surface. Our water molecules experience these seasonal changes. They are warmed by the summer sun. They are cooled by winter winds. They rise and sink with the mixing currents of winter storms. And then, on a warm day, perhaps in late spring or summer, something begins to happen to some of the water molecules near the surface. The sun shines down on the ocean's surface. Its energy, traveling 8 minutes from the sun to Earth at the speed of light, warms the water. This energy causes water molecules at the surface to vibrate more vigorously, to move more quickly. Some molecules move fast enough to break free of the hydrogen bonds that hold water in its liquid state. They leap from the surface into the air above. This is evaporation, the transformation of liquid water into water vapor. It's happening constantly, everywhere on the ocean's surface. In some regions more than others, evaporation is faster in warm, dry areas and slower in cool, humid areas. But it's always happening. The ocean is constantly releasing water vapor into the atmosphere. One of our water molecules evaporates. One moment it's part of the ocean, connected to other water molecules by hydrogen bonds, moving in the collective motion of the sea. The next moment, it's free, a single molecule, surrounded by air, moving independently. The water vapor molecule rises. Warm air from the sun-heated ocean rises, and the water vapor rises with it. The molecule is now part of the atmosphere again, back where our story began, though it doesn't remember its previous time in the air. Water molecules have no memory. Each moment is new, unconnected to what came before. The molecule rises through the boundary layer, the lowest part of the atmosphere where turbulent mixing is strong. It rises into the free atmosphere above. It might rise a few hundred meters. It might rise several kilometers. The height depends on the strength of the upward air currents, on the temperature difference between the surface and the upper atmosphere. As the air rises, it expands and cools. The pressure is lower at higher altitudes, and in lower pressure, air expands. following the ideal gas law that governs the behavior of gases. And when air expands, it cools, its energy spreading through a larger volume. The rising air, carrying our water vapor molecule, cools toward the dew point, the temperature at which the air becomes saturated and can hold no more water vapor. And then, once again, the cycle begins. The air cools past the dew point. Water vapor begins to condense. Our molecule encounters a condensation nucleus, perhaps a crystal of salt, lifted from sea spray, dried and left drifting in the atmosphere. The molecule attaches to the nucleus. Other molecules join it. A cloud droplet begins to form. The cycle is complete, and yet it has no completion. There is no end, only a continuation. Our water has traveled from cloud to earth to ocean and back to cloud. It has taken weeks or months for this journey, but the journey is not unique. Every water molecule on Earth has made similar journeys countless times. Water is old. Not just old in the sense of existing for a long time, but genuinely ancient. The water molecules on Earth formed billions of years ago. Some arrived on Earth during its formation, carried by comets and asteroids from the outer solar system. Some formed here as hydrogen from the early atmosphere, combined with oxygen in the hot, volcanic landscape of the young planet. The water you drink is the same water that dinosaurs drank. The same water that fell as rain on the first forests. The same water that flowed in the rivers before rivers had names. The same water that filled the first oceans when the earth was young and the moon loomed larger in the sky. Water is not created or destroyed in any significant quantities on Earth. It simply moves, cycling endlessly through the environment, changing form but never changing its essential nature. Ice to liquid to vapor, and back again. Ocean to atmosphere, to land, and back again. Our single drop, the focus of our journey tonight, is not special. It's one of countless drops, all on their own journeys, all cycling through the same pathways, all part of the same grand circulation. The water cycle operates on many timescales simultaneously. Evaporation and condensation happen in moments. Raindrops fall in minutes. Rivers flow for days or weeks to reach the sea. But water in glaciers might remain frozen for thousands of years. Water deep in the ocean might not return to the surface for a millennium. Water in deep groundwater, in aquifers isolated from the surface, might rest for 10,000 years before emerging again. The fastest parts of the cycle and the slowest parts of the cycle exist simultaneously. Water moving at every possible speed, on every possible timescale, all at once. Most water is in the ocean, 97% of it. About 2% is locked in ice, in the great ice sheets of Greenland and Antarctica, and in mountain glaciers around the world. Less than 1% is fresh water available at the surface or in the ground, and only about 0.001% is in the atmosphere at any given moment, existing as water vapor or as cloud droplets. And yet, that tiny fraction in the atmosphere is crucial. It's the water that cycles most quickly. It's the rain that falls on the land, the rain that fills our rivers, that waters our crops, that replenishes our groundwater. All life on land depends on this tiny fraction of Earth's water, making its endless cycle. Water is neutral. It has no preference, no goal, no intention. It simply responds to physical forces. It flows downhill because of gravity. It evaporates because of heat. It condenses because of cooling. It freezes at 0 degrees Celsius and boils at 100. These are not choices. They are simply what water does, what it must do, given the laws of physics that govern our universe. This neutrality is, perhaps, restful to contemplate. Water does not worry about its journey. It does not fear the dark depths of the ocean or the high cold reaches of the clouds. It simply exists and moves and changes form according to the conditions it encounters. In this sense, water is the perfect subject for a meditation on nature. It's everywhere, constantly moving, essential to life, and yet entirely without consciousness or concern. It simply is. Every glass of water you drink contains molecules that have been everywhere. Some were in the Pacific Ocean last year. Some were in the Amazon rainforest last month. Some were in clouds over Antarctica. Some were in the groundwater beneath the Sahara. Some were in the bodies of whales, or trees, or bacteria. Some fell as rain on Shakespeare's head. Some were drunk by Cleopatra. Some were in the tears of people whose names we'll never know. Water connects us all, across time and space. The same water, cycling endlessly, shared by all living things, linking past to present to future in an unbroken chain of motion and transformation. And so our journey ends, though it never truly ends. The water continues its cycle, as it has for billions of years, as it will for billions more. Moving from sea to sky to land and back to sea, falling and flowing and evaporating and condensing in an eternal round. Perhaps you've been drifting as this story has unfolded. Perhaps you're already asleep, in which case these words reach you only as distant sounds, meaningless but perhaps comforting in their gentle rhythm. Or perhaps you're still awake but drowsy, your mind quieted by this long, slow story of water's patient journey. Wherever you are in your own journey toward rest, you can let go now. The water will continue its cycle without you. The rain will fall, the rivers will flow, the ocean will receive them, and the sun will draw vapor back into the sky. All of this will happen, has happened, is happening, in the eternal present of the natural world. You need do nothing but rest. The water knows its way. It always has. It always will. And so can you trust the natural rhythms of your own body, the cycles of sleeping and waking, of tension and release, of thought and rest. Let yourself drift now, like a water molecule in the ocean. Let yourself rise and fall with the gentle currents. Let yourself simply be, without effort, without striving. Rest. The water will continue its journey. And when you wake, it will still be raining somewhere, still flowing in rivers, still evaporating from the ocean's endless surface. The cycle continues, always, and that's enough. Rest now.